class. Recall that last time we agreed that the action of any subgroup of SL2R or PSL2R on the upper half plane U will be said to be properly discontinuous or properly discontinuous in the weak sense if any of these two equivalent conditions is satisfied, namely that the group acts with discrete orbits and finite stabilizers. That's one way of saying it, or that for every point in the hyperbolic plane there is an open neighborhood with the property that only finitely many elements of the subgroup may have the property of not taking the neighborhood sufficiently far away. So we said that the action would be said to be properly discontinuous or properly discontinuous in the weak sense. Right? In the weak sense, because here we say finite rather than being on this set being only the identity, and here we say that the stabilizer be finite rather than requiring it to be to consist only of the identity element. Okay, of course these conditions are on both conditions are equivalent and are on the action, right? They are conditions on the action of the subgroup. And today we are going to see that these conditions on the action actually that we can deduce some topological property of the group itself from these actions, from these properties of the action, from the action being properly discontinuous. So first, let's start with an easy exercise. So let pi be the projection from SL2R to PSL2R, and take any subgroup of SL2R. And the exercise consists in showing that that gamma being discrete or its image under pi being discrete are equivalent. And okay, that is that gamma is discrete if and only if pi of gamma is discrete. And notice that this has as a consequence, that this exercise 85 has as a consequence that if now I give you a subgroup of PSL2R, then that subgroup is discrete if and only if its inverse image under pi is discrete. Okay, so and then this allows us to make this definition. So I'm going to say that a discrete subgroup of SL2R or PSL2R is a Fuchsian group. So people usually define the notion of Fuchsian group as being a discrete subgroup of PSL2R. But since I'm going to be switching back and forth between groups of matrices and the groups of Mobius transformations that they determine, I allow discrete subgroup of SL2R to be called Fuchsian groups, although I don't think this is the standard practice. Okay, so take a subgroup of SL2R or PSL2R, right? So I'm going to consider either the action of matrices via Mobius transformations on U, or directly just the groups of Mobius transformations. And so for such a subgroup, the following are equivalent. And it's that gamma is discrete, so it's a Fuchsian group, and its action on U is properly discontinuous. Right? So gamma acts with discrete orbits and finite stabilizers on U. So, which is not the same as saying that the action of gamma on C bar has discrete orbits and finite stabilizers. Not necessarily. Just the part involving U, the part of the action that involves U. So, okay, so this is an if and only if. So let's show the two implications. So suppose gamma is discrete and take an element of U. So we want to prove that its orbit is discrete and its stabilizer is finite. So to prove both, I mean take a compact subset, any compact subset, and what we're going to show is that the intersection of the subset with the orbit of Z naught is finite. So now this inverse image is compact. We have already proved it, and so this is the set of elements of SL2R, you know, that take Z naught into K, right? So when I intersect with gamma, what I obtain is the elements of gamma that take Z naught inside K, right? So since this one is compact, and gamma is discrete by assumption, this intersection is finite, right? So only finitely many elements of gamma take Z naught inside K. But so that automatically implies that the points of the form gamma Z naught for gamma in my subgroup capital gamma, that there are only finitely many of them inside K, right? Because only finitely many elements of gamma, of capital gamma, take it inside K. So only finitely many of them are of that form. So this intersection is finite. But and actually, kind of, I know it's finite because actually its cardinality is actually less or equal than the cardinality of this set. And it's less or equal depending on whether the stabilizer of Z naught is trivial or not. Okay, but so this is finite. So what we have proved is that for this arbitrary point, the intersection of its orbit with any compact subset of U is finite. So this implies that the orbit is a closed discrete subset of U. So otherwise, it would accumulate in some point in U, and then taking a point in U, which is a point of accumulation of the orbit. I can take it and then take the union of that point with some sequence of elements of the orbit converging to it, and with that I can form a compact subset of U whose intersection with the orbit is infinite, in contradiction with this that I have already shown. Okay, now notice also that if I take K to be Z naught itself, this intersection gives me precisely the stabilizer, right? So because it gives me the elements of gamma that take Z naught into Z naught, so that take it to itself. So it would be the stabilizer, and so but this intersection is finite, right? So the stabilizer is finite. And this finishes the proof that 1 implies 2. Okay. Now for 2 implies 1, I'm going to do it by a counter positive. So I'm going to assume that gamma is not Fuchsian, and then I'm going to show that it cannot happen at the same time that the orbits are discrete and the stabilizers are finite. Okay, so suppose it's not discrete. Suppose gamma is not discrete. So it has an accumulation point, and that accumulation point I can take it inside itself, right? So it's because being discrete is not accumulating inside oneself. Right? So okay, so it has an accumulation point and a sequence that converges to that accumulation point. being a cumulation point, I can assume that the elements of the sequence do not repeat, so they are all pairwise distinct. Okay, but then of course then I perform the usual trick, which is to write the identity element of gamma as a limit of elements of gamma. And they are, and you see, these elements are all pairwise distinct because these were pairwise distinct. Okay, now because since the function f z naught is continuous, this specializes to z naught being this limit, right? I mean, and this is because of this f z naught is continuous. Okay, but now you see here this sequence has all pairwise distinct elements. So this means that at most one of them can be the identity. So without loss of generality, I can assume that none of them is the identity, right? By chopping at the beginning of the sequence if necessary. Okay, but then you see, right? So this means that if the orbit is discrete, then so if the orbit is discrete, so this sequence, the sequence of the sequence of evaluations at Z naught has to be stationary, right? Has at some point to be just equal to Z naught. Okay. So at some point, it must contain all elements to be equal to Z naught. But you see, all of these are pairwise distinct. And so, this way, what we obtain is that there exist infinitely many distinct elements of gamma that fix Z naught. So, the stabilizer is finite. So what do I see? That it cannot be that the orbit is at the same time discrete and the stabilizer finite. Right? So one of the two conditions must fail. So this shows that 2 implies 1 by counter positive. Okay. So we have then this theorem that you see somehow I would say that the importance of the theorem is that it characterizes an intrinsic property of the subgroup, namely being discrete, in terms of the action, in terms of a geometric action of the group. So, in particular, this tells me that this action has a lot of information about the group, so much information that I can at least deduce this topological property from this action. Okay. Now examples. Well, I start with some obvious example, right? I mean this one, SL2Z. So the 2 by 2 matrices with integer coefficients and determinant 1 is of course discrete, right? Because all the entries are integers, so they are like very far away from each other. Okay. So it's discrete, and so is PSL2Z, right? So all the Morris the group of all the induced Morris transformations. Of course, if I have a discrete subgroup, then any subgroup of it is again discrete. So these I would say are like obvious examples. Some other examples that are slightly more involved is that if you take any parabolic or hyperbolic element of PSL2R, then the subgroup generated by that element in PSL2R, so not in SL2R, in PSL2R, is Fuchsian. So this is an exercise. It's not very hard. So I leave it as an exercise. Another exercise is that if you give me an elliptic element, then the subgroup it generates inside PSL2R, so the subgroup of Mobius transformations it generates, is Fuchsian if and only if that subgroup is finite, right? So for an elliptic element, the subgroup generated by it is Fuchsian if and only if the element has finite order. Okay, and then you see, so far these are kind of very simple examples. So the question is there a way of producing more interesting examples? Like, is there a method to produce them? And of course, if we are asking for a method to produce such interesting examples of Fuchsian groups, of course, I'm kind of also tacitly asking or implicitly asking for a criterion to decide whether a given group is Fuchsian or not, right? And it would be nice to be able to decide, if I give you certain, let's say, a finite subset of PSL2R or of SL2R, it would be nice to just by seeing this finite subset, being able to decide whether the subgroup they generate is Fuchsian or not. And so we are going to answer this question. There is a very nice answer, which is, I would say, a very powerful answer, which is yes, there is such a method, and there is such a criterion, and it's Poincaré's polygon theorem. That what it says is that if you start with a certain hyperbolic polygon and a certain set of Mobius transformations pairing its sides, satisfying some mild conditions, then you can assert, you can be sure that the subgroup they generate is Fuchsian, and much more. I mean, it's a theorem that gives a lot more information. But this will be in a future chapter of the course. We are not going to answer it right now, so it's just a promise that there will be such an answer. Okay, so that's it for today. And so the next thing I'm going to do is I'm going to study some algebraic properties of elements of a Fuchsian group, and in particular, I'm going to prove that there is no Fuchsian group, there is no Fuchsian subgroup of PSL2R, so there is no discrete subgroup of PSL2R isomorphic to the free abelian group of rank 2, so to Z direct sum Z, right? Z plus Z. So in other words, this is never a Fuchsian group. This free abelian group cannot be realized as a Fuchsian group, and this as a Fuchsian subgroup of PSL2R, let's say, at least. And this will have as a consequence that it is not possible to obtain the compact torus as the orbit space of the hyperbolic plane by the action of a Fuchsian group. So this has like a very strong consequence. That is that compact tori cannot be approached with hyperbolic geometry, or they do not admit hyperbolic structures. But I'm getting ahead of myself. The content of next class is that there is no Fuchsian group isomorphic to Z plus Z. Okay.